is a purple line here. This purple line here is also due to the standing wave of this refracted light. Okay, and also you can see there's some like the PAC. If you check this color, it's like a blue. Okay, this light blue color here. That you have the bleaching effects. Okay, and also also this reflected light, you can see this some partially exposed material happened here because now you have PAC. There's a little bit PAC here, which means it did get some exposure here. Right, it's underneath this mask, and that will cause your light width to increase. Okay, just change this color. I mean, the color here just become the orange instead of red, which means a part of this resist reacts with your photons. These photons from the reflected light due to this slow cycle here. And that will cause, after your development, your line width will increase. Okay. Now we try to how can we calculate this PAC, right? The concentration of this, and okay, so now in the following slides we will introduce the exposure part. Okay, so we try to use the absorption coefficient, this alpha, to model the light intensity in the photoresist. Okay, so this is the Z direction we have. Okay, so this is the PR photoresist here. So your light, when it penetrates through your photoresist, during the transmission of your light, your part of the light is absorbed by your resist, and then absorption part is your PAC will change to this carboxylic acid. Okay, and that will change to the acid. Okay, so and also due to the bleaching effect, we need to consider this alpha not only a function of Z but also a function of time. Okay, so this alpha resist, we can write it like this is related to a certain coefficient times the concentration of your PAC. If you have more PAC concentration, this photoactive component, then your absorption coefficient will be larger. But once this PAC reacts with your photon and change to acid, then you become more transparent. So that's also the function of Z of your alpha. Okay, so if we want to calculate the total I, then we can do this exponential, we can do this integrals. Okay. And now we try to model this photoresist. Okay, so this is the concentration, and the photoresist, the absorption depends on this how many material we have. So we use M to define the percentage of your PAC. So originally, if M equals to 1, which means it's unexploded at time 0. So this one equals to 1. So all the PAC will be the original one. So this PAC 0 means that in the time equals to 0. In the beginning, you have such amount of PAC in your resist. And once you begin to expose, and M will become to drop because you have less and less PAC component left in your resist. Okay, so this alpha will depends on the M, which means how many PAC you have. And we use two coefficients A and B to help us to define the properties here. These two parameters we call DO parameters. Okay, and we'll see similar things when we move to oxidation in the next chapter. There's some parameters like this will help us to define the equations that can help us to understand what's going on in the experiment. Okay, so we have A, the absorption coefficient of bleach, and B is the unbleached resist, which means that if M equals to 0, that means the resist is fully exposed. So this one equals to 0, your alpha resist now will become only B only. And B is a constant, accounts for the non-bleached resist. Okay? Those resists will still give you some absorption. Okay? And A will be the absorption coefficient, the parameters of the bleached materials. Okay? And now we can understand equation 24 and 25. Okay? And now, since this M is a function of time, right? So we can take the derivative and say, okay, this derivative can be related to your C, related to your intensity and your remaining ratio of the PAC. Okay, and by defining a parameter C here, C is also another DO parameters. Okay, DO is the name, okay, the guy who first wrote the papers to define this relationship. Okay, so this we can plug this 24, this equation back to 23 here. Okay, back to these equations with this alpha equals to A times N plus B here. So we have these equations like this. Okay, and now we can combine 26 and 27. Those are a couple equations because this is the intensity change with your time, and this is your PAC change with your time. But this M also related to your I here, and your I change with your time also related to your N here. Okay, so by solving this couple equation, these rate equations, we can solve simultaneously your intensity and your M. Okay, so that's why we can get something like this plot. Okay, but this again we have to define these ABC parameters. Otherwise, we cannot solve these equations. Well, how can we get these ABC constants? Okay, we can get this by doing some experiment. Okay, so here we can design an experiment like this. Consider we have a photoresist, the thickness is D. Okay, and we put it on a transparent substrate. Okay, and then we can use the exposure system to give a certain amount of light, and then here at the back side we have transmitted light, because they're going through this resist and going through this transparent substrate. We have transmitted light. We can use a detector to measure this the intensity of the transmitted light. Okay, and from the figures on the right hand side we show here, we can continue to increase the dose time. Okay, so we increase the total amount of exposure dose, and maybe in the beginning we can compare the intensity here and this intensity IT here. Okay, by comparing these two, we know the transmission coefficient. Okay, and because your transmission plus this, if there's no reflection, then plus this absorption should be 1. Okay, if you have some air coating, then we don't have reflection. Basically, the light going through here, part of it get absorbed, and the rest of them get transmitted, and you can take the transmitted light intensity. Okay, so once you increase in the beginning, if you have like 0 dose, there's a certain amount of transmission you have. So by increasing the exposure dose, which means that more and more PAC can react with the photons now and become more transparent. Okay, so that's the bleaching effect that we described earlier. So once you increase the dose to like a certain amount of dose number, and you can see that the transmission will become a constant, which means that you already those PAC inside this certain amount of resist has already exposed and changed to acid, and they won't absorb anymore. Now your absorption coefficient will only have this B right now, right here. Right, so this one will not reach to 1, transparent will not reach to 1, because this material still provides certain of absorption here. Okay, so by doing this, we can change the thickness, we can change the exposed, we can get this transmission index T0 and T now. So we get to fit these numbers, and we can have these parameters ABC here. Okay, so once we plot this, we can have our A, our B, and our C. Okay, so those are the number of time, or the D, the thickness that we can change in this experiment. Okay, so once we have this ABC, we can plug it back to this equation 26 and 27, then we can solve this couple equations. Okay. Okay, now we'll try to model the post exposure baking. Okay, this baking before you develop your resist can help us to smear out the edge of your resist pattern. Okay, so this we can generally we can model this as a simple diffusion process. Okay, so you can see that the textbook will give you more explanations here, but we can just define this diffusion constant here as a D0, and also you have E8, which is the activation energy. By writing this diffusion constant as this Arrhenius form, then it's quite common that when we define some physical parameters, usually it's defined in this form. Okay. So since here we have the concentration distribution in space, then once you provide heat then we'll have some interdiffusion happens. So after this a certain amount of time and temperatures, we can see this this color contour change to this, and we won't see any staining effect as we show on the left-hand side figures. Okay. Okay. Now we come to the development of your resist. Okay, so in the textbook there are several models has been proposed to explain the development, and but the simplest one is purely empirical, which proposed by Theo. Okay, the same guy that this give you this local developing rate. This rate will be a function of your x, y, z, and also the function of your m, which we had defined earlier is a ratio of your PAC. As time goes by, then those E1, E2, and E3 are also empirical constants, which means that you can do some experiment to extract these numbers. Is not totally like an analytical form of these constants. So we have to do this, get these numbers by doing some experiments. Okay. So that's the rate, and we can also use some more physical models. These models are based on the experiments. But we can also try to model this using propose some physical models. Okay, and this model proposed by Mack, which used to model the developer diffusion and reactions. Okay, can be explained like this. Here is the resist. Okay, the thickness is D, and this is the substrate. And here are the developer, and you can consider this molecules of these chemicals, their concentration CD is here, and also the CS is the concentration near the surface of your photoresist. So there exists some slope or difference, okay, because those chemicals will react with the resist at the surface, right? So you can imagine that the concentration will be smaller or lower at the surface. Okay, then we can use some concept of flux to explain this. Okay, the first flux is F1 that counts for the diffusion of developer, which means that your chemicals moving in your solutions when it diffuse to the surface of your resist. Okay, and this diffusion will depends on certain constant and the concentration difference between these two. Okay, so we can write this as KD times CD minus CS, which there's a concentration difference that provides a gradient. Now, so you have diffusion happens, right? Okay, so that's the very simple idea of diffusions from high concentration to low concentration area. Okay, and the second flux is the F2. So the first one is try to move from here to here, is the F1. The F2 is the surface reactions between your developer and resist. Okay, so we can write a chemical formula to explain this. Okay, we can write a constant and also the two concentration numbers, CS and PAC. I think this is fundamental high school chemistry, we know this. Okay, so in a steady state, is F1 equals to F2. Okay, F1 equals to F2. So we can get some simple, arrangement of these equations. And at that time, we define that R, which is the rate of your equals to F1 F2. Okay, so we can do some simple calculations here and we can plug this PAC using M that we defined earlier to explain this. Okay, so we get these equations. The final equation looks like this. So M equals to 1, which means the unexposed case. So M equals to 1, this one will reduce to 0, and we have R minimum. Okay. And which means that your material is not exposed, so they have certain amount of reaction rates, like maybe 1 or 2 nanometers per minute or per second. I don't remember. You can check the previous slides, right? But once you fully exposed, the M equals to 0, which means you don't have any PAC left. Okay, so in that case, you have R maximum, which means that can be react with your developer very fast. Okay. Okay, so you can use the TK tool to see this development process. Okay, so we can adopt the figures here, which we exposed, and after certain condition of our post-exposure bake, then we can put it into the developer. Okay, so this is the pattern developer for 60 seconds. Okay, here will be the after 60 seconds. And in the center, just in the part way through the development. Okay, and this after 60 seconds, we complete the development. So from here, you can see that because we have last PAC during this in this purple color region, then which means there's more acid, okay, more exposure resist there. So that will react with the development faster, to give you the faster development rate. Right? This R give you the faster development rate. So if you monitor this, maybe for example, this is probably 30 seconds. Okay, just for example, then you can see part of this are gone, which means they have faster development rate, reaction with your developer. But here it will be slower, but eventually they are gone. Okay, and also you can see there's a part of this area has been partially exposed. Okay, that will also affect a little bit your line width here. Okay. So that's the general idea of expose and develop your resist. Okay. If you are a device guy or processing guy, then if you have this idea, it's easier for you to find the optimal parameters when you try to do the exposure and development. Like for example, my students, sometimes they suffer this kind of issues. They have to do a lot of experiment, but if you don't know the physics behind it, it's very difficult to get a correct recipe because you got to spend a lot of time doing experiments. Okay, now let's probably try to wrap up this chapter. Okay, again, these future trends I left here on purpose because now you can understand what's really going on after this 10, 20 years development of technology. Okay, so now you can check that. So this probably the one that we are using, and also this. Okay, is applied, well known right now. And UV, okay, that's the outgoing technology we have right now. And some resolution has enhancement technology, and but for here, like E-beam, L-beam, X-ray, imprint, they are probably for research only, research purpose only. Okay. Okay, so yeah, we talk about like EUV. The SML and Harvard that make this kind of tool, right? And there's a university in Harvard. There's a dean that she visited us like 2 weeks ago, and she's trying to make a summer school, trying to build a summer school in this summer. And so they came to NTU and talked to us and say, okay, maybe SMU is very interested in doing this, and also maybe try to find TSMC, and we try to find Taiwan students, and also students from India, because the president of SML said, you try to find students. Originally, the team tried to find a student from MIT to do this summer school together, but the president of SML said, the student from MIT probably won't come to here to work for us. The student from Taiwan or from India probably they are very possible to come to work for SML in New Zealand. In Holland. Right. So we'll see. If I have more information, I will probably let you know, that you guys maybe will be interested in that summer school. Okay. Okay, I think that's the part of this chapters, and let's move on to the next one. Will be the oxidation. It's good that we're still on a schedule. Okay. Okay, let's see. So in this chapter, we will introduce the thermal oxidation, and also some properties of the silicon and silicon dioxide interface. I think this interface is very important, because that's mainly the reason that we use silicon as the material for the IC industry, because we are making the MOS structures, and if there's some interface defects or issues, then your gate will have problem to control your channels. Right? So originally we have silicon and silicon dioxide that's very stable and very low interface state. So that will help the transistor to function normally. Okay. Okay. So here's just the figure show you that. Here we show you the oxide thickness. Okay. So we have thick oxide. The purpose is to use as an electrical isolation. For example, like low-cost process that we introduced in the first chapters. Okay, and some masking oxide or PET oxides. Okay, that can be used for mask or for pad to like stress release. And